So activity 20.14, which is on page 505 of our textbook, is called Discovering Pi. And in this activity, you have students measure different circles. You can like have them just pick out different circles around the room, and you're gonna need to have a string available for each student, string or yarn, something that's not gonna break apart really easily. And they can each have their string, and they also need a ruler, or I said just a meter stick, because if the circles are bigger, it's easier than like having to like measure 12 and then add on like 12 plus 12 plus 12 every time. So they walk around the room with their string, and probably a partner too, because sometimes they need help holding things. And so they take the string and they first measure the circle, or I'm sorry, the circumference of the circle, and they can just kind of line it up around the base of something, and then they need to pinch off where it ends on the string like this. So now they know that this length is the circumference of the circle, and then they need to measure. You might need to review some ruler skills ahead of time. For students with learning disabilities, or who like need it to be a little more simplified, you might just say measure to the nearest inch, because in this activity that'll still get them relatively accurate data. But for students who are a little more advanced, you could say you need to measure to the nearest 1/8 of an inch or 1/16 of an inch, depending on how specific the ruler measurements are. So this says it's about 11 inches. So on my chart that you're going to give them, give each student one of these tables to fill in. I'm going to write down that the circular item was the vase, and its circumference was about 11 inches. And now I need to get the diameter of the vase, so they could like pick it up like this and make sure that one edge is down. So like this is why it might be really helpful to have a partner in this activity, so that one person's like ensuring that the string is straight and going all the way across the circle. So I'm going to pinch it off on the edge over here, and then I know that's my diameter. Line it up on the ruler, and it says it's 3.5 inches. So then over here, you can write 3.5 or 3.5 inches. And I used to do this activity when I taught 5th grade, so I think it's pretty appropriate for that grade level. At this point, you know, they've probably heard of Pi, they've probably heard of Pi Day. A lot of teachers celebrate that, but they may not really understand where that number 3.14 comes from. So what we're having them do is figure out two pieces of the circumference formula. Remember, circumference equals diameter times pi, which they don't know yet. They don't know this they don't necessarily know what this number is or what it represents, and they don't necessarily know the formula yet. We're just trying to get them to make observations about this relationship between the circumference and diameter of circles. So here's one example, and then it asks me divide circumference by diameter, and so they'll need a calculator at this point, and they'll type in 11 divided by 3.5, which is, this one's very close, and most of your students probably won't measure as accurately as I did, so it might not come out to be right at 3.14, but this one was very, very close. Okay, so I have some other objects here that I'll quickly do another example for.
Please.
Is 3.07. Another thing that I've done in the past is like sometimes I make a big deal out of Pi Day, and so on the students' desks I'll make up a bubble solution that you can either buy a bubble solution or you can mix like soap with some water and dilute it, and then on their desks you can spread out the soap solution if you've got desks like that are pretty big. Then I give each student a straw and have them blow bubbles. In the soap solution, which is really fun, and they like the challenge of like seeing who can make the biggest bubble, but then it all really comes down to the same idea of measuring these other objects where they need to measure the circumference and the diameter of the bubble. I usually put this chart up on my board because I think it's fun when they're like getting the data and they run up to the board, walk slowly up to the board and write their data on the chart, and then they can see what other groups are gathering too. And at some point in the class, someone usually says, it seems like a lot of the numbers in the column that says divide circumference by diameter are really close to 3. And especially if your students are measuring pretty well, that will happen. And they're not all going to be really close to 3.14, but they'll be pretty close to 3. And then you can have this conversation about like, why do you think it's always showing up close to 3? And do you guys know of a number that's really close to 3 that people talk about a lot? And depending on the level of your students and like how much they know about pi, that conversation might sound a little bit different. But you can get them to see that like, this is how pi was discovered in the first place, was this relationship between the circumference and diameter of all circles. And then you can have this conversation about going back to measurement about, well, why didn't all of them end up being exactly 3.14 if we know that the circumference divided by the diameter is always 3.14? Another nice thing you can do is bring it back to the formula. And so now if they know that pi is supposed to be 3.14 for all circles. So if they know that circumference divided by diameter is supposed to be 3.14, or we could write like C divided by D is supposed to be 3.14, how could we figure out, if we know the circumference of a circle, how could we figure out what the diameter is? And if we know the diameter of a circle, how can we figure out what the circumference is? Because it was a lot easier to measure the diameters. So if we want to know the circumference, like if we're building like a circular fence, we would really just need to measure the diameter, because we know if we turn this equation around, now D times 3.14 is going to be the circumference. So if I can easily find the diameter, I can calculate what the circumference is going to be. Activity 20.17 has an activity sheet that goes along with it that you can print out, and there are 3 different triangles on there, and it suggests printing out 3 copies of each triangle and giving like a group a set of these 3 sets of congruent triangles. And the teacher can demonstrate, or the students can kind of have some time to explore how when the 3 different angles of the triangles are lined up together on a line, how they form a straight line. And if students have been exploring different kinds of angles, they'll probably know that a straight line, an angle that forms a straight line, is 180 degrees. So you can kind of review those concepts of like what is a straight angle, what's an acute angle, what's an obtuse angle. And so if the teacher, has demonstrated that they can line up, or the students have discovered that you can take the 3 different angles and line them up and make 180 degrees, then you can pose this question: will all triangles do this? Like, are there any triangles out there that won't, if you line up their 3 angles, they won't form 180 degrees? And we're also trying to get kids to recognize that, like, this angle plus this angle plus this angle. So like the three angles that are lined up are adding up to 180 degrees. Kind of pose this challenge, like, can anyone find a triangle for me whose angles don't add up to 180 degrees? For students who, this might be more of a challenge for, students with learning disabilities or students who struggle with math, it might be easier from the get-go to have them label, to have the three congruent triangles all oriented the same direction, and have them label the angles, like all the top angles are A. All the angles on the left are angle B. And then all the angles on the right over here are angle C. So that when they're trying to line these up, they can be sure that they're getting three different angles, because in some triangles, either the angles are the same, like you may have a triangle with two of the same angle, or they may look very similar. So up here, they're making sure that they get an A, a B, and a C to see that those three angles add up to the same thing. When I taught 5th grade, we had this as a standard. This is saying this is an 8th grade standard, but when I was teaching 5th grade, like 3 years ago, it was a standard for 5th graders to understand this, and I would do this thing where I would like confiscate a triangle's angles. So I would take the triangle and I would actually rip its angles off. I would make like a giant triangle that I put up on the board out of paper, and I would go up and I would rip the angles off of each triangle. So like here's angle A, here's angle B, and here's angle C. And then I would take those angles and I would line them up on a line. And so I would have kids make triangles. I would have them like as a challenge, try to make a triangle whose angles I couldn't confiscate and make a straight line out of. And eventually they realized, like, oh, it's gonna be true for all of them. We don't have any evidence that it's not. And for some groups it takes a little bit longer to convince them, and for others it doesn't.